$50 and was able to identify 43% of the patients in the database using things like demographic information, zip codes, the way they paid their bill, their doctor's name. And really, I mean, she was doing some super sleuthing, doing internet searches for news stories that matched that information, right? So the key there, the key culprit in these privacy breaches is this auxiliary information. And so that's where the trouble comes in. You might think that the information that you released doesn't breach anyone's privacy, but you don't know what other information is going to be able to be linked to that. And so for a hypothetical example, imagine that a professor here at RPI releases the following statistic in an article that they write. You know, of 1,723 freshmen at RPI, 155 of them have parents whose total parental income is less than $30,000 annually. So I don't think there's anything that could be really more de-identified than just this aggregate, right? 1,723 freshmen at RPI, 155 who meet this criteria. But the problem is, if there's another professor who releases a similar statistic, you know, maybe their research is completely different field, but is also, you know, parental income is relevant to their research as well. Another statistic released shortly thereafter that only differs by one this time, 1,724 freshmen, 156 who have parents with less than that income. Somebody seeing both of those may then start to, you know, try to find, well, did we get one new freshman in the middle of the year? And they might, you know, be able to find out again through this outside auxiliary information that yes, no freshmen left the university, one new one transferred in at exactly that time frame, and now that individual's privacy has been breached. So research was before this idea of differential privacy, there were, you know, different questions about how much can we guarantee people's privacy? What should be the level of privacy guarantee? And there were some suggestions motivated from cryptography, specifically a notion called semantic security, which I'm not familiar with, but basically from what I've read, it suggests that in cryptography, you can have something called perfect secrecy, which means that no information can be learned about the plain text from the ciphertext, despite any amount of auxiliary information. So an example given there on the screen is that if an adversary knows the entirety of the message that has been encrypted, except for one piece, which is, say, an important location, then even having all of that auxiliary information of this whole message decrypted except that one piece, and having the ciphertext, those two things together are not supposed to be allowed to be able to break that if there's perfect secrecy. So the question is, can you have such strict guarantees on privacy? And the work of Cynthia Dwork and her colleagues show that no, perfect privacy is not possible. They've showed this formally using Turing machines, which is another thing that I'm not very familiar with, so I'm not going to show the proof, but just to briefly mention it, they modeled any supposedly private query mechanism along with modeling the adversary, the auxiliary information generator, and the privacy breach decider all as Turing machines, and were able to show that in their situation that privacy was breached. So I'm not going to go through the mathematical proof of that, but I'm going to give an example that they give in plain language. So imagine that you have something like IQ score that people feel is a private piece of information about themselves that they don't want to be made public. But you have people who are willing to voluntarily take place in research where their IQ is recorded and put into a database that needs to be protected. So if an adversary learns that John Doe's IQ is exactly 17 points lower than the average of adult Caucasian males in the US, That's the auxiliary information. But they have no idea what that average is, then therefore don't know John Doe's IQ. Well, a query which reports that average would give the adversary exactly the missing information they would need in order to learn John Doe's IQ exactly, right? So here you have a specific example of a kind of contrived example, but of where certain piece of auxiliary information matched up with a query that I think most of us would consider is not privacy, a breach of privacy. Those two things together allow the adversary to learn, this information.
So what you're not. So the assumption here is, or what's not being said is, well, what if we, instead of giving out the details of everybody's IQ, what if we just give them summary statistics, right? That'll preserve privacy. And then what you're saying is, well, you have that, but if you also have this information about John Doe's relative to this information, then it actually spoils the privacy.
Yeah, exactly. So basically what this is all leading to is the idea that what counts as auxiliary information that we need to protect against and what counts as an actual breach of privacy. In any given example, we all intuitively feel whether it is or is not a breach of privacy, but how do you define that in a way that is applicable to situations that you haven't already considered? And so this is all leading to the definition of differential privacy, especially with this odd example. What they talk about in what Professor Dork talks about is that the analogy with semantic security is a false analogy. So in a cryptographic setting, you have at the top there, you have your secured data, and it's being transmitted, encrypted to a recipient that has a key. And if you have an adversary who eavesdrops on that message, they're not supposed to be able to learn anything about that plain text from the cipher text, since they don't have the key. Whereas the recipient will get the useful information, will get the plain text, because they have the key. Well, in the bottom setup, you have the statistical database setup. So you have secured data, and it's being transmitted, but instead of being transmitted encrypted, it's being transmitted through some privacy-preserving mechanism. But the reason why it doesn't match up with semantic security is the recipient is the same as the potential adversary. So you don't have a recipient who has a key and an adversary who doesn't have a key. You just have one person who's receiving that message. What you would like for them to be able to do is get useful information from that query, but only useful information about the population, not about any particular individuals. But the challenge there, what makes it different than semantic security is, whereas in the cryptography setting, the adversary is not supposed to be able to get any useful information. Here, the adversary is supposed to be able to get some useful information. You just want it to be useful information about the population and not about individuals. And so, yes. So I guess what I'm trying to say is the term adversary, in the cryptography setting, you have an intended recipient of the message, and the adversary is someone who's not supposed to be receiving the message. In the statistical database example, when we talked about this idea of perfect secrecy, there you don't have these two different people. What you have is a database that has information in it, and you want people to be able to query the database and get useful information, but you just want it to be useful information about the population and not about individual. And so sort of naively, people would originally think like, okay, well, if I just query and get like the average value, and if I get the average value of 10,000 people, the average IQ, that's not giving me any information about any one individual, so there's no breach of privacy. But the challenge in that, if you reported that average to enough decimal places and reported it exactly without any noise, then 2 average queries that were on databases where just one person was added, you would be able to exactly compute that value for that one person. So you would have a breach of that person's security. Yes, yes. So that's where I think Professor Dwork talks about the semantic security analogy being a false analogy, because whereas originally you had people who were suggesting, motivated by cryptography, that we should be seeking perfect privacy, she was saying that's not possible because the setup is different. In cryptography, the adversary is a different person than the intended recipient of the message. In the statistical database setting, the intended recipient of the message is the person that you.
Everybody's a recipient.
Yeah.
Some are good actors.
Yeah. So there's no intended recipient that has a key and adversary who doesn't have a key. It's just you want the recipient of the query response to get useful information about the whole population, but you don't want that same person to get any information about the individual people on it. Mm-hmm. Oh, no. When I say semantic security, this is a term that I'm not especially familiar with, that was in Professor Dwork's research, where the idea of semantic security was that in cryptography, no matter how much auxiliary information the adversary has, all of that auxiliary information and the encrypted message together, they're still not supposed to be able to learn anything about the plain text.
In cyber security, there's 100% those are the 2 classes. This, everybody's a recipient with what they, because everybody can get access. And you may have classes of access.
So I think a lot of the research before 2006, I don't know about after 2006, but reading the paper from 2006 by Professor Dwork and her colleagues suggested that prior to that, there was a lot of overlap between the people who were looking into protecting privacy and the people who studied sort of cryptography. And so there were people who suggested that the same level of protection that we have in terms of secrecy in cryptography, we should be seeking the same level of protection. And I think her work suggested first that that's not possible.
People prove that these privacy models are not sufficient for one. Yeah. I think that Watson is the first to be the first one.
Yeah, I definitely don't know. It seems from all of my reading that this seems like one of the most widely adopted, but I guess I don't really know for sure. But so this example where I think everyone would agree John Doe's privacy was not breached in this sort of contrived example kind of motivates the idea of differential privacy, because one thing to note is that if the adversary had this auxiliary information, then this query, which reports the average IQ score of adult Caucasian males in the US, that query would be pretty much the same whether or not John Doe's data was in the database. And so the idea is that if John Doe's data was not in the database, then a query to that database couldn't have breached John Doe's privacy. And so what all of this leads up to is that, which queries to a statistical database would result in a privacy loss. We might all have an intuition to begin with, but hopefully these examples show it's not as simple as your intuition might lead you to believe because of the open-endedness of what could be considered auxiliary information. And so to remove this ambiguity, you would need to have a precise definition of what does it mean for someone's privacy to be breached or preserved. And so in that last example, you had this idea that if a mechanism is privacy preserving if a query to that database, the return value has a probability that isn't changed much by whether that person's data was in or not in the database. Sorry, say that again.
So by this from the word, what I understand, your data wouldn't have been, the data was not.
Yeah, that's what I'm saying. No. So that's definitely not what I'm saying. So what I'm saying in this one example, I'm just saying if John Doe's data is not in the database, then a query to the database cannot breach John Doe's privacy, right? And so, in this example here, the return value of this query, which is the average IQ, the return value would not be changed much whether John Doe's information was in or not. And so perhaps it'll be most clarifying for me to just show you this definition. So the definition of differential privacy is that you have some randomized algorithm, and on any databases that differ in just one row, the return value of that random algorithm, the probability of achieving a certain return value isn't changed much. And by much, what I mean is there's this multiplicative factor e to the epsilon, right? So if I have databases D1 and D2 that differ on at most one element, then the probability of the output of the random algorithm on D1 being in some set S is less than or equal to e to the epsilon times the probability of the return on D2 being in S. And so here, if epsilon is a small positive number, e to the epsilon is just a little bit more than it's approximately 1 plus epsilon. So the idea is the return value isn't changed much. So you can know if I give my information to this database, it's not going to, any query to the database is going to output about the same answer as if I didn't put my information. Well, so that exactly is one of the strengths of differential privacy. So if you have some other notion of privacy, there might be people who think that their technique is private because the database has 1 million people in it. But if the database was small, maybe it wouldn't be as private. But differential privacy, it doesn't matter the size of the database. What is more important that we'll see in a few slides is the type of query. And so let me give you a concrete example to show you. So assume that the domain of your random algorithm consists of databases with just a single column, and a query returns the number of rows that match some criteria. How many people have an IQ less than 90 or something? So the query to the database would return the correct value perturbed with some noise. And how much noise you add depends on how sensitive, and I'll define that in the next slide, the function is. But so, for example, in this one, if we output a value given by this probability distribution, this is the Laplace distribution, where it's centered on mu I for database I. So this mu I would be the correct value. And so it's a double exponential decay. So if you output a response that has this probability distribution, then you can prove mathematically that it's differentially private. So here's how you would do it. So any two databases, D1 and D2, that differ on at most one row, the correct answer would could only differ by a maximum of one. Right? Because like if you have database D1 and you know 87 people have an IQ less than 90, database D2 only differs in one row, then the number of people with an IQ less than 90 would have to be 86, 87, or 88. Right? And so based on that, when you divide for any real number x, the PDF of the response on database D1 divided by the PDF of the response on database D2, and using this property of exponentials, and then the triangle inequality, since mu2 minus mu1 differs by at most 1, you would get that this ratio is bounded by e to the epsilon. So this is the crux of what it means to be differentially private.
So when we say differentially private, go back to there. So it's actually, it's epsilon,
Yeah, epsilon differentially private.
Yeah.
Yeah, so if epsilon is a small positive number, then it's fairly private. If epsilon is an extremely large number, you know, it's not very private, even though it's still epsilon differentially.
Epsilon is something the process.
You decide what you want epsilon to be, or as I'll show later on, if you create an algorithm that's composed of many steps, you keep track of how much privacy is lost at each step, and then the overall algorithm would be epsilon differentially private, where epsilon equals the sum of all those.
Well, I guess what I was trying to go down is epsilon is something
Yeah, so there's the two sort of techniques. You can either decide on an epsilon that you want and then add whatever noise that you need to guarantee that, or you can keep track of how much noise you add and then at the end calculate what your epsilon was. So, I mean, you could design your own differentially private mechanism, but this one right here, this is a differentially private mechanism. And so if you query this, each time it would output a different answer. Now, and this is something I was going to talk about later. So obviously, if you query this same exact query multiple times, then you'll eventually be able to narrow in on the correct answer, right? And so what happens is, there's a law of composition for these differentially private mechanisms that says that if you do many mechanisms in a row, the total privacy loss, that's what they call the epsilon, the privacy loss, is the sum of them all. So if you have an epsilon differentially private mechanism that's 0.1, but then you query it 10 times, well, now your epsilon is 1. And for the most part, all of the papers that I've read by Dr. Dwork are agnostic to what value of epsilon you should use. She says it's based off of your needs. Most of the work that I've read suggests it should be less than 1 or approximately equal to 1, no, not much more than 1. So they suggest anywhere from 0.1 to ln of 2 or ln of 3, that kind of thing. Although the one paper ends up getting epsilon 8, which is not a very small value. Other questions about what this means right here? Okay, so how you figure out how much noise to add actually has nothing to do, well, I can't say it's nothing. it's mostly to do with the query function itself. So they define something called the sensitivity of the function. And what that sensitivity is on any two adjacent databases, what's the maximum difference that the true response would have. So like on this example that I gave before, right, you're counting the number of rows that match some criteria. If you have two databases that are the same except in one row, well, then the number of rows that match that criteria in database one can only be, at most plus or minus one from that of any other database. Does that make sense? And so based on the sensitivity of the function, that tells you how much noise to add. And so for any function that has a bounded difference, then you can achieve differential privacy by just adding the appropriate amount of noise. And so that's what her paper in 2006 was all about, calibrating noise to sensitivity and private data analysis. It was how much noise do you need to add? And the answer is just straightforward. If you add Laplacian noise that has a standard deviation proportional to epsilon over the sensitivity of your query, then you've achieved differential privacy. So some of the nice properties of differential privacy, right? It's unambiguous. It has a precise definition, so you don't have to just sort of hand wave argue, well, I think my algorithm is private. You can rigorously guarantee that it matches differentially private. What that means in terms of real world privacy, you might have to interpret, but in terms of mathematically, you can prove whether or not an algorithm is differentially private. I think it's somewhat intuitive that, as an individual, if I choose to allow my data to be in a database, then the probability of any particular output of a query can't change by too much, as opposed to if I didn't have it. So this is related to some concept called plausible deniability. I don't know if anyone's heard of it before, but they mentioned that, like in the social sciences, if you were to ask individuals a question that was a yes or no answer, it's kind of awkward, right? Something where if I say yes, I'm embarrassed. A technique is you have them flip a coin twice, and only they see if it lands on heads or tails. If the first coin flip landed on heads, then they answer truthfully. If the first coin flip landed on tails, then they answer based on their second coin flip, where heads means yes and tails means no. So that way they can do this coin flip, and if they're supposed to report honestly, they can say yes without feeling too embarrassed, because you don't know if it's really yes or they're just answering yes because they flipped tails and then heads. Right? So that gives them plausible deniability, and the same concept is in differential privacy, because if somebody does a query, even that same query that I gave before about 1,000 or 155 RPI students versus 156, the answer wouldn't be the truth. The answer would be the truth perturbed with noise. So even if it differed from 1 week to the next, you wouldn't know if it differed because a new student was added or if it differed because of the random mechanism. That's a plausible deniability. The other two very important properties of differential privacy, one is it's immune to post-processing. So if somebody does a query and it's differentially private, epsilon differentially private, and then they give you that output, there's nothing that you can do to it that makes it less differentially private, no matter what auxiliary information you have, just based off of the definition of differential privacy. There's no function you can do to it or no way you can change it to make it less than epsilon differentially private. And so that's really good for synthetic databases, right? So if you have a training data set and you train your your machine learning algorithm, your GAN or whatever, and it's epsilon differentially private, then you take that output and give it to somebody, there's nothing they can do to it that'll make it less than epsilon differentially private. And then, like we already talked about, the very important property is composability. So if multiple queries are performed, then the total algorithm the privacy loss of the total algorithm is just the sum of the privacy losses of all the steps. So if you have an algorithm that consists of multiple steps, each one you can compute the privacy loss because they're simple steps, and you can easily compute the privacy loss, the maximum possible privacy loss of the whole. And so before I go any further, I want to see if I communicated this at all well, and see if anybody has any ideas on whether the following are differentially private or not, and why. Okay, so my first example is you have a domain that consists of database with a single column of numeric data and 1,000 rows, and the query trims off the lowest 100 values and the highest 100 values, and then averages the other 800 values. Turns that trims mean. That's, you know what?
So you can see that if I add another, and I want extra layer, and that data can be used.
Yeah, absolutely. So the way that I stated this, definitely not, because it's a deterministic query. I didn't say anything about adding any sort of noise. And the only way a deterministic query can be differentially private is if it outputs the same exact value for any two adjacent databases. So here, if I had, exactly like you said, if I had database 1 that had 1,000 rows and database 2 that had 1,000 rows, and one of those middle 800 values was different, well, the output of this one is deterministic. So with 100% probability, it's going to be whatever its value is. And the output of this one is going to be with 100% probability, a completely different value. So when you divide, probability of 1 by probability of 0, you can't do it. And so not differentially. So that two things is, one is, if it's a deterministic algorithm, it can't be differentially private unless it's like a constant. And number two is, if you have a query that has a probability of returning a certain value of 0, then, and there I guess I'm talking about discrete probability, then, or if the PDF is 0 at a certain point, I don't want to get into measure theory or something, but then any adjacent database would also have to have a probability of 0 returning that because of the ratio aspect. Okay, so changing it up, adding noise. So you have a domain that's, again, databases with a single column of numeric data, still 1,000 rows, trim off the top 100 and the last 100, and it returns the average of those 800 values with noise added, either Laplacian noise like I did before, or Gaussian noise with some constant value for the standard deviation. Guesses? So it turns out, actually, it doesn't matter how high you make the standard deviation. If it's constant, then it will not be differentially private, as I stated it, just because I didn't put any bound on the possible values in the database, right? So any sigma that you pick for the standard deviation, you can find two adjacent databases if there's no bound on the entries, where this one is 1,000 zeros. It's going to return 0 plus some noise. This one is 1,000 values of a Googleplex. Yeah. So last one, very similar.
Why does the removing
matter? It doesn't.
If you're fuzzing it, why does it matter now that you're?
So I just it doesn't really. I made the first example be that you were removing 100 rows to kind of trick people to think, I mean, I personally, before I did any of this, before I've ever read about differential privacy, if you told me if someone's information is in a database and somebody returns the trimmed mean of the values, the trimmed mean of, you know, weights or something like that, is that private, or was anybody in that database's privacy breached? Let's say, like, what could be more private than trimming off the highest 100 and lowest 100 and returning a trimmed mean? I mean, that's just a statistic, you know, not very informative statistic. I don't know. But so that I added the trim part just to kind of throw people for a loop.
What if the trim is different? What if the trim randomly removing two? Always, whenever I query.
Different.
Yeah, it's always a different, or it's always a random selection.
Yeah, I'm not sure then. Well, anytime, you know, this one's deterministic. So anytime you're doing something probabilistic, then you would have to just try to prove, and you might be able to prove that it's epsilon differentially private with a not very small epsilon. I don't know. But so this last one, very similar, trim the top 100 and lowest 100 off, but then you clip the remaining 800 values to be in the interval C1, C2. So if any of the values are less than C1, you make them C1, and if any of the values are more than C2, then you just make them C2, and then you return the average of those 800 clipped values with noise out. So the clipping is the key to making it differentially private. So the difference is that now I know that if I have database D1 and database D2 that differ on at most one row, then the maximum difference between that one row's values is C2 minus C1, right? Because like if let's make it heights of people, right? So heights aren't really normally distributed, right? Because nobody has a negative height. So let's say if anybody that, I mean, you could just assume that nobody's taller than 120 inches or whatever that is in centimeters, because nobody has ever been taller than that. But so if you say all of the values for my heights are between 0 and 120 inches, now you can compute the sensitivity of that query function, right? Because the trimmed mean is only going to change by a certain amount, which would be 120 divided by 800. That's like the maximum that it could possibly change. So, I mean, in this example that I gave, you're doing a trimmed mean. It doesn't even have to be a trimmed mean, but the key is that you have to clip the values. So if you returned, even if we just ignored any trimming, you just took all of the values in your database, but you clipped them, and then you average them, and then you add noise. You can add the amount of noise needed to make it epsilon differentially private. And the clipping, what that does is it allows you to compute the sensitivity. So if I go back to this slide right here, the sensitivity of your query function is the most it can change on adjacent databases. And so if you have two databases have 1,000 rows and 999 of those rows are the same, but one row is different, if the values all have to be between 0 and 120, then the average value on 1,000 values can only change by 0.12, 120 over 1,000. So because you know then your sensitivity of your query function is 0.12, then to make it epsilon differentially private, you can add Laplace, a noise with a Laplace distribution that has a standard deviation proportional to epsilon divided by 0.12.
true whether or not any clipping actually occurred.
Yes.
All the values are actually
Oh, yeah.
between 0 and 100.
Yeah, exactly. Yeah.
No clipping actually occurred because of that.
Mm-hmm. Yep. That's the Hamming distance. It's yeah. Any two databases, X and X prime, that yeah. It's saying that sensitivity, when you compute the sensitivity of a query function, a random algorithm, or whatever you want to call it, when you compute the sensitivity of that, that's a Lipschitz condition, because what it's saying is that the maximum difference of a query on X and a query on X prime divided by the distance between X and X prime is always less than or equal to the sensitivity of that function. So this leads exactly into running out of time. This leads exactly into a very simplistic technique for doing differentially private machine learning, which is just that as you go through your training data, if you first partition the training data into disjoint batches, and then for each batch, you compute the gradient of the loss function at each point, and then you clip the gradient. That's the key there, which means if the norm of the gradient, the loss function for that one data point is larger than some constant c, and you decide what c should be, then you divide it by its own norm over c. And once you clip the gradients, then you average all the gradients for that batch, and you add noise with a high enough standard deviation to make that batch epsilon over p differentially private. And then because you do that p times, that adds up to an epsilon differentially private in algorithm. You decide. So if the gradient, is a vector in all of your weights, the gradient of your loss function, then like if you add Gaussian noise, then they use the 2 norm, and you decide, what's the largest 2 norm you want, and that's your constant c. And for any data point, if the 2 norm of the gradient for that data point was larger than that, you just scale it down. You scale down for each individual gradient, each individual point. And then you average all the gradients for that batch, and then you add the noise to that batch. And then after you do that, you go through and do that for all the batches, and then you can pass through the data as many times as you want.
Tell me if this is a
Mm-hmm.
The effect of the clipping, to me, is in a way a statement that the data range is bounded, and I know what that bound. Going back to what you were talking about in the fights,
Mm-hmm.
even if no clipping actually occurred, you bounded the range from 0 to 100.
Yeah, exactly. I mean, that's the point of it. Is in that example with the heights, or in this other example where I don't know a bound on the numerical values. If I don't know a bound on the numerical values, I can't compute the sensitivity of the function, so I bound it. Yep.
Now, you often know a lot about the data. Not with any, still be able to calculate.
Mm. Yep. If you know what the values should be, then you can clip. And so this was a very simplistic approach, but I jump ahead since I'm kind of running out of time. In this paper, Deep Learning with Differential Privacy, they do basically this, But they mentioned in their paper that even though they list their pseudocode here with a constant value C, because they do deep learning with multiple layers, they actually use different values of C at different layers and different values of the standard deviation of the noise. And so what they do is they use the approach that instead of picking the epsilon and adding however much noise I need to add to achieve that epsilon, they use something called the privacy accountant, where as they train their algorithm, they're choosing values of C and values for the standard deviation of the noise, but they're keeping track of how much privacy is lost in each step. And then at the end of the entire algorithm, they output the values of the weights for their model and the overall privacy cost.
What they're clipping is the weight itself.
No, they're clipping the gradients, not the actual weights.
Right.
Mm-hmm. But really, I mean, what epsilon differential privacy means in this context, like any others, is that if you had some training set at the start of it all that was different from your original one by just one row, then the epsilon tells you how likely you, how much more or less likely it could have been to get the output that you got on this data set compared to the other data set. And so the idea is, you know, if you have one person with HIV of some ethnicity, of some gender, and some zip code, whatever, them voluntarily being in your health database isn't going to change the outputs of your GAN. And so then when you use that GAN to construct a synthetic database, you know, their information shouldn't be any more likely to be in there than it would have been if they hadn't. I shouldn't say any more, very little more likely. Yeah. I mean, the output is the weights. In this case, the output is the weights associated with your neural network. So the probability of these outputs on two adjacent databases wouldn't change by much. Although, again, I say by much, but strangely to me, in this example, at the end, in their technique, their epsilon is 8. E to the 8 is about 3,000. So the probability of an output on two databases that only differ on a single row could change by almost 3,000. It's the probability of any two outcomes. The probability of getting an outcome on one data set can't be very different than the probability of getting that same outcome on a different data set.
So it's kind of flipping the whole space from the get-go. It's kind of like that C1 compute that you did.
Mm-hmm.
So it's got to be in there, and it's not going to go out of there. You could force the algorithm to bring in projection or something.
Mm-hmm.
Of course, if you're never allowed to go out, if you take a step out of there, it's going to come back.
Mm-hmm.
So
So it sounds like what you're saying is then instead of clipping the gradients and then adding noise to the gradients, you would potentially clip the weights and add the noise to the weights.
yeah, I would just say, okay, we did. It's always, you're just never allowed out, so it's always in the span.
Mm-hmm.
The answer W is always in the span. You can never leave. So it's kind of like the one where we clip it. Like we're gonna, but we just clip the output, not the gradient.
But if you clip the weights themselves, you automatically eliminate the possibility of certain models from having.
But we do that routinely.
I'm not saying we don't, but if you clip the gradients, though, not really limiting types of models.
I even don't really understand the proof of the gradient, why the gradient stops the weight from moving. I have to understand.
So,
All it does is each step of this algorithm, you know, you're accessing the training data, and then when you access the training data and you do this step, it has a true answer of what the output should be that is based off of the average of the gradients. But you add noise to it so that it's a random. I mean, I guess in a sense it's already random, but you're adding noise to the true answer so that you have this randomness to it. And then to prove differential privacy, you have to add the level of noise that's based off of the sensitivity of this, which is the most it can change on two similar databases. So in terms of doing it here in this step, where, if I'm hearing you correctly, you would just do it here, where instead of adding the noise to the gradients, you would do your descent, but you would do your descent with noise. Like you would have to.
I guess you could take the step, flip it, then like, because then you wouldn't allow yourself the beta. It's never allowed to too far, right? It's not allowed. So if you want to go too far, we could do that. And then I add noise after. I mean, that would be, I don't know, that's okay, but that would be more like reservation.
yeah, I was going to say, and regularization, I mean, you're just trying to slow things down, and I think that's what flipping the gradient does. It doesn't mean you can't ultimately get to a certain weight. It's just you can't get there in only one step.
Yeah, I mean, they mentioned in this paper that people often clip the gradient for other reasons, but here you are able to achieve differential privacy by flipping the gradient and then adding the appropriate amount of noise. Yes.
Right.
And they do a lot in their paper in terms of hyperparameter tuning to figure out what's the appropriate balance. Like, the goal is to achieve something which, you know, has the level of accuracy that you would want from your machine learning algorithm, while somehow not busting your desired privacy budget, they call it.
So this algorithm combined with your previous machine learning naive algorithm kind of got me thinking about federated learning and differential privacy.
I don't even.
Yeah, so you have batch size, right? So federated learning, the batch size will be one, right? I know that the size doesn't matter, but
Well, the size here, I didn't talk about it, but they had something they referenced called the privacy implication theorem, where because they're taking this random sample that has this sampling probability, then instead of epsilon delta differentially private, you can multiply by that q, and it's q epsilon q delta differentially private. So it might be applicable there.
We're at 7, so you probably can.
Okay, and no other questions? All right, thanks.
Oh, that's it?
Yeah, that's the end.
So thank you very much, Joe.
Yeah.